Okay, welcome to a new question and answer session. I think Giovanni has asked the following question, if I understand the question well. Well, we've been through a RG decimation process or simplification process of our Fokker-Planck dynamics, which somehow allows us to ignore the fast dynamics which enters in the local thermalization. And if I understand the question, he's raising the point, is this corresponding to finding an effective theory in which somehow I've smoothed out all these terms here in favor of some kind of renormalization of the remaining constants? So, well, the answer is no. What this mirroring procedure that Giovanni is probably referring to is actually something you could do. And we have done actually in a paper of ours, which I might even be able to find as we speak. Let me say if I can find it. Right, yeah. Let's say RG. Yeah, this one is the first paper. There's a couple of follow-up. Let's see if this can show up. Okay. And in this paper, what we do actually about 10 years ago was to apply really a renormalization group theory on the space of, on the dynamics of the Fokker-Planck equation, and starting from the Langevin equation, and then we go through what is called the Wilson renormalization group, which is essentially a field theory methods to quantum field theory method adapted to this problem to smear out the dynamics to a lower resolution. And the result is an effective theory which contains additional interactions that you can see here, which are derived from the underlying dynamics by integrating out some hard frequency shell in the frequency representation of the dynamics. But that's not what the Markov state model approach is actually doing. Markov state model really defines an entirely different Hilbert space. If you look at the original Fokker-Planck dynamics, I think it's convenient to phrase it in terms of the Hermitian components. Now, if you think about the Hermitian components, all your dynamics is defined by an imaginary time Schrödinger equation. And this wave function is really, you can introduce a Hilbert space just as you do in quantum mechanics by introducing position operators and eigenvalues. And then the wave function is nothing but the position projection of some quantum state, which, well, the fact that I call it quantum state is simply because I'm using the same Hilbert space that I use in quantum mechanics to define states of my system, which happens to be a classical system. Why not using a Hilbert space? Now, if you do this, then of course you have your wave function, and your wave function obeys this Hermitian version of the Fokker-Planck equation. What we do when we define a Markov state model is to project the dynamics on a discrete space of states, and the new states, called the microstates, are one for each basin. And if you want, you can define them in terms of local wave function, where the local wave functions are nothing but the local Gaussianity weights, the local Gaussian weights, times the the characteristic function of the basin and the root of the partition function. Now, basically, what you do by solving the Markov dynamics is calculating, projecting your state onto this basis, and this will give you something like a probability as a function of I. Psi is your state. And then you look at the dynamics of this state. Now, this is the Hermitian analog of what we have been doing in non-Hermitian components. So maybe I should call it differently. Maybe I'll call it like psi. And it's the Hermitian analog because I've used the Hilbert space of the Hermitian part of the Hermitian formulation of dynamics to relate position eigenstates and densities to states, simply because the bracket notation is particularly convenient only if you are in an Hermitian formulation, because in the Hermitian formulation, bra behaves like an inner product over the adjoint of a ket, which is of course just a notation thing. We know the bra is a dual operator and the ket is actually a state vector. But okay, I think I clarified that. What we are actually doing is imagining the system has, you know, I'm now in 2D. The system has a basin here, then has a basin here, then has a basin here, and so on. And it jumps from basin to basin. Then what you're doing basically is replacing this picture with one in which you say, okay, this is one state, this is another state, this is another state, and this is another state. And then basically you have a network of state, 1, 2, 3, 4, and then you have a network of connectivity, and each arrow represents the transitions probability or there's a transition rates between each of the states. So in this case I would have N1, N2, N3, and N4 being the 4 probabilities of finding the system in any of these states, irregardless of what specific configuration the system might visit within each state. And each of these probability can be obtained as a sum over J of the corresponding rate matrix. And the strength of this connectivity, how fast this transition occur, enter in this particular matrix element, rate of transition from 1 to 2 to 2 to 1, from 1, 3 to 2, and so forth. So all the relevant information is in this Chi-AJ matrix. I hope I clarified the question. But if you read in notes, you should be able to find this.